That's taking in food, breaking it down to molecular sized pieces, taking in food, breaking it down to molecular sized pieces, extracting the energy, and synthesizing different structures you need. Synthesizing different structures that you need. You eat food, you break it into pieces, you burn the energy, you use the pieces to build parts of your body. Digestion. Now metabolism, you guys you've all heard metabolism before, but it's probably not the definition you're thinking. Metabolism, sure, it means how much energy you burn. You know, people say, oh, she can eat 2 giant hamburgers and not gain an ounce, and I eat a freaking French fry and I gain 10 pounds. That's not what we're talking about. Here, metabolism is the sum total of all of the chemical reactions that go on in your body. Metabolism is the sum total of all the chemical reactions that go on in your body. Excretion is the next one on the list. Excretion is removing waste. We have lots of chemical reactions going on in our body, and we end up with stuff we don't need. Those are waste products. We have to get them out of our body. Otherwise they build up and become toxic. So excretion is removal of waste products. Next on the list, reproduction. Now, in order to continue as a species, we have to produce offspring. We have to make babies. But you don't have to have a baby to be alive. The reproduction you're doing is in your body. It's reproduction of cells. You have cells in your body that are constantly dividing all the time. You get a brand new stomach lining about once a week. Everything in there is replaced. Your skin cells are constantly growing, dividing, making more skin. Now, other cells don't do that. You have cells in your body that have been there since you were born and will be there until you die. Cells like neurons. In your body, we'll talk about this when we do cells too, I'll say it again. But in your body, there are neurons, especially like in your sciatic nerve. They're this long, runs from about here all the way down to your toes. You got a cell that's this freaking, multiple cells in your body that's this freaking long and lives forever with you. You got other ones that are disposable. They reproduce all that. Does that make sense? Is it okay? Next up is growth. Sure, that is getting taller. Growing, but also cells get bigger. Cells get bigger too. So that's growth. Those are necessary life functions. Survival needs are pretty immediate. You need them right now. Without them, you're going to be in trouble in a matter of minutes or days. Survival needs include nutrients. Again, you need fuel. You need energy to keep all this stuff organized and working. So you need nutrients. You need oxygen. That's probably the most pressing survival need on that list. We all know that if we don't have oxygen for minutes, we die. You know why? chemically.
Well, congrats, oxidative.
You're definitely on the right track. You're definitely on the right track. There's one specific chain that's really important. Anybody know what I might be talking about? Go ahead. Yeah, absolutely it is. Yep, generation of ATP. How many guys have heard of ATP before? How many know what it stands for? You're so close. Adenosine triphosphate. Yes, good job. Adenosine triphosphate. That's your body's fuel. That's gasoline for your cells. Without ATP, your heart stops beating. Without ATP, your neurons stop firing. Your brain shuts down. You need oxygen to make enough ATP to keep systems going. No oxygen, you don't make enough ATP, boom, you die. Oxygen is really important survival need. Water is the next one. Water is really important too. If you're in the wrong environmental conditions, you can die within even 24, but definitely 48 or 72 hours if you don't get water. Our bodies are anywhere between 45 to 70% water. 45 when you're really old, 70% when you're a new baby. You can tell because when you're old, you're all wrinkled and you're kind of out of water. And when you're a baby, the water comes out everywhere when you're sleeping. But we need water. Most importantly, water participates in chemical reactions. Most importantly, water participates in chemical reactions. It also provides a place for chemical reactions to occur. It also provides a place for chemical reactions to occur. We are a giant bag of wet chemistry. Without water, we can't do the chemistry we need to stay alive. Normal body temperature. What's normal body temperature? You should know this. 90.6. Good. What is it in degrees Celsius?
37.
37. All right. Yes, you should know both those numbers. If you're going into the sciences, you have to have a tiny amount of the metric system. If you have me for lab, had me for the first lab already, you know that they're sneaking the metric system in on us, whether we like it or not, right? How many guys like, oh, metric system is terrible, I'll never use it. Go ahead, put your hands up. It's cool, you are using it. They started a while ago with 2 liter bottles of soda. 2 liters is about half a gallon. I mean, just because just as easily could have made a half-gallon bottle of soda. It's about the same size. Well, I don't want to drink a half-gallon of soda, but 2 liters is fine. They're doing it now with water bottles. Can I borrow your water bottle for just a second? I don't know, but I'm guessing. Yeah. How much water is there in English? Anybody know without looking at your water bottle? 16.9 ounces. What's up with the 0.9? It's really 500 ml. Half a liter. You can put 4 of those in a 2 liter bottle. So they're already sneaking it in on us. Just out of curiosity, anybody know how many mLs is in a 12 ounce can? I think it's 354. Then don't worry about conversion. Just start using the metric system. 37 degrees Celsius is your normal body temperature. 98.6. What happens if your body temperature goes up to 99 degrees? Nothing. You go walk around a block in the summertime, it's above 99. What happens if your body goes up to like 105? You're not doing real well. You might start seeing stuff, weird delusions and stuff like that. But if you have a fever, there's colds going around right now, and flu even. If you have a fever, your temperature's like 101, what should you do? Oh my God, take aspirin? No. First of all, I'm not a doctor, don't listen to anything I say, okay? But just let it cook for a little while. Running a fever at 101, 102 is your body's natural response to get rid of the critters. Speeds up your metabolism, makes things go faster for you, and harms the pathogens. So a little fever isn't bad. Now if you're cooking at 104, 105, 106, talk to somebody. If your kid A lot of you guys are gonna have babies, some of you may have them now. If your kid's cooking along at 104, 105, go somewhere to get help then. Much better to get help when you don't need it than not get help when you do. But normal body temperature 98.6, life is good. And finally, appropriate atmospheric pressure. Appropriate atmospheric pressure. We are under pressure right now. You guys feel like you're under pressure right now? You are. The air is pushing down on you. And it's pushing down on you with a pretty good force. Anybody know how much atmospheric pressure we're right now? First of all, get it out of the way. One atmosphere, yeah. One atmosphere pressure, yeah. Go ahead. Beautiful, awesome, yes, 760 millimeters of mercury. Also about 14.9 pounds per square inch. So for each square inch of your body, there's like almost 15 pounds pushing on it. Almost 760 millimeters of mercury. Does anybody know what your blood pressure is right now? On average, what's your average blood pressure?
120 over 60.
Like 120 over 80 is like average. 120 millimeters of mercury over 80 millimeters of mercury. What the heck is a millimeter of mercury? Anybody know? Anybody ever see old medical instruments? It's like a glass tube with mercury in it. That's how high it goes. They measure how high that column, that stack of mercury is. That's where we get millimeters of mercury from. So, lots of different measuring units, but we are under pressure. Constant pressure. If we are placed in an environment where there is no pressure, what happens to us? Yeah, we start to expand our blood boils. How many guys saw Total Recall, not the new one, but the old one with Arnold Schwarzenegger? He gets jetted out onto the surface of the planet, his eyes are popping out. That's not really how it works, but it's not gonna be very good for you. There's lots of space movies where their spacesuit gets ventilated, they lose pressure, and they intrude into the strawberry jam. We're not sure exactly if that happens or not. We know it's not gonna be good, but we've never put anybody out there and exposed it to hard vacuum. So hopefully it stays that way. But we need pressure to keep us in. Water and blood is gonna boil under really low pressure situations. So that's survival needs. That's what we need to stay alive. And also what we need to maintain life. All right, homeostasis. Homeostasis and control mechanisms. Homeostasis is probably a new word for you guys. How many of you guys have heard of homeostasis before? Nice. How many of you guys use homeostasis in your regular daily conversation? Not so many. All right. Homeostasis is basically this. Homeostasis is the ability to maintain normal conditions in a changing environment. The ability to maintain normal conditions in a changing environment. Straight out of the book, the ability to maintain relatively stable conditions even though the outside world is changing. The ability to maintain relatively stable conditions even though the outside world is changing. We were just talking about an example of that. Your body temperature. Your body temperature stays right around 98.6. That's normal. If you're outside cutting the grass in August in the sun, is your body temperature going to be 98.6? It's going to be elevated. But we're going to do some tricks to keep from dying of heat stroke. What tricks are those? We're going to sweat. And that sweat gets on our skin and it evaporates and it carries heat away from us. Now, let's say it actually gets sort of cool here over the next month or two. Like if it drops down below 60 degrees, oh my gosh, everybody has their Uggs on. Oh, it's so cold. What does your body do when it gets cool? You shiver. And that muscle movement, that muscle doing that, makes heat. And that warms you up. You shiver when you're cold because it makes your muscles do this, and muscles actually generate heat. So we use different tricks to maintain our body temperature. That's called homeostasis. And there's lots of other factors in our body that are maintained that way. Our blood sugar lower for one, blood pH, all kinds of stuff is measured and controlled. That process is called maintaining homeostasis. You guys all right? Questions? All right, now, homeostatic regulations, we have to have a regulatory mechanism. Open up your books to page 10. Turn to page 10 if you're not there already. There are three main components that help us maintain homeostasis. The first one is a receptor. The receptor monitors the environmental conditions. The receptor monitors the environmental conditions. The receptor passes that information on to the effector. The effector is the second part of that loop. The effector, second part of that loop. I just told you the wrong thing. Sorry, I'm kind of on autopilot this morning. I apologize. I don't have enough time. The receptor sends the information to the control center. Sometimes I think about all this stuff when I'm lecturing and I just totally mess up. So if I'm saying something that's weird, tell me. Okay. The receptor sends the information to the control center. The control center decides what to do about that information. Control center decides what to do about that information. The receptor says, oh, it's getting kind of hot. Hey, control center, check it out. Control center says, I know what to do. Control center tells the effector, hey, effector, do this thing. The effector is what changes whatever variable it is you're controlling. The effector changes whatever variable it is you're controlling. Let me give you an example. You guys will find out. Is that your phone? You want to just sing your zippy sound? Or do you want to sing more?
Zip, zip, zip.
3 more.
Zip, zip, zip.
Yay! Alright. I'm a terrible artist, so I don't mind drawing stuff on the board. You guys can laugh. It's okay. This usually ends up looking a little like a penis. And I apologize for that. That's a thermometer. In your house, you probably have air conditioning. Maybe. And this is how that works. you're gonna have a thermometer. Thermostat. And an AC unit. If the temperature here goes up to 76 degrees, that sends information to the thermostat. By the way, if you know anything about HVAC, this is not correct, but it's going to give you an idea. Sends a message to the thermostat. Thermostat says, hey, we're too hot. And that sends a message to the AC, turn on. Which one of those is the receptor? Thermometer. Which one is the control center? Thermostat. Which one is the effector? AC unit, right. Does that make sense? Everybody's okay? All right. Now take a look at page 11. There are two different methods of homeostatic regulation: positive feedback and negative feedback. Positive feedback and negative feedback. The first thing you have to get out of your brain is negative feedback is bad. It is not bad. Negative feedback is not bad. Positive feedback is not good. Erase that. Delete. Negative feedback goes against the stimulus. Just write that down even if it doesn't make sense. Negative feedback goes against the stimulus. It'll make sense in a minute. Negative feedback tries to return a value to its normal point. Negative feedback tries to return a value to its normal point. Our body temperature regulation is a great example of negative feedback. When we're out pushing a lawnmower in July or August, our temperature goes up and we sweat to bring it back down again. And then when we go inside and sit in front of the AC and the fan, it's like, ooh, it's a little cold. No, that's exaggeration. You get cold and it brings it back up again. That cycling back and forth close to a set point is negative feedback. Negative feedback tries to keep the values close to a set point. Does that make sense to everybody? Most control systems in your body are regulated by negative feedback mechanisms. Most control systems in your body are regulated by negative feedback mechanisms. Positive feedback mechanisms work with the stimulus. Just go write that down. Positive feedback mechanisms work with the stimulus. They go in the same direction as the stimulus. They will increase whatever action or activity is going on. They will increase whatever action or activity is going on. There are a few positive feedback mechanisms. The two major ones we're going to discuss, we're going to use as examples. Everyone take a crack at it? Yeah, labor contractions, good. Labor contractions. Getting the baby out. When you start contractions, baby's head will kind of move down and press against the cervix. That will send a message to the pituitary glands to release oxytocin. Oxytocin is a hormone. If you're in a hospital, they call it oxytocin. Releases oxytocin. Oxytocin makes smooth muscle contracts. The uterus goes like this and contracts, which pushes baby's head against the cervix, which releases more oxytocin, which makes the uterus contract. Over and over and over and over again until what breaks the loop? Then it comes out. And we break that positive feedback loop. Positive feedback is going to increase the stimulus until something breaks it. So childbirth, contraction, is one example of a positive feedback loop. What would happen if your body temperature was set up to be a positive feedback loop? You'd burn up and die, yeah. Because you get hotter, it makes you get hotter, you get hotter, it makes you get hotter, boom, 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 done, see ya. The other positive feedback loop that I want you guys to think about is coagulation of blood. Coagulation of blood is a positive feedback loop. Does anybody know what components, what parts of blood help clot? Yeah, good. Platelets. Platelets are these little chunks of chemicals that float around in your blood. Now, when it gets exposed to things like torn blood vessels, collagen, and tissue, they do what's called degranulate. They go like this, and they get all spiky. They look just like Sandsburg. They stick together, and one platelet releases chemicals that cause like 10 more to go. And then those 10, it's like 100 more all over the place, and it makes a plug to fill the hole. That's a positive feedback loop. Anybody see a problem with that? Yeah, it's a bad day if you cut your finger and your whole arm clots. So there are mechanisms in place to keep it localized. We learn about that in AP2. As a matter of fact, my AP2 class is going to look at that tomorrow. But the initial coagulation reaction is a positive feedback loop. And if you look at page 12, there's even a picture of it. Homeostatic imbalance means something's wrong somewhere. Your receptor might be a little wonky. Your control center might be damaged. You're not putting out the right output, bless you. Your effector might not be working effectively. But there's some kind of disease process, some kind of issue going on. If you have homeostatic imbalance, you're sick. Something's not right. That's homeostatic imbalance. Questions, comments, concerns? Everybody okay with homeostasis, positive, negative feedback, all that stuff? Good. By the way, that stuff's kind of important. When I say stuff like that's important, what does that mean to you? It's going to be on a test or quiz. Alright? I don't say it all the time, but when I say it, I mean it. Language of anatomy, anatomical position. Look at page 13. That dude is in anatomical position. Anatomical position is this. Anatomical position is a common frame of reference, so we can talk to somebody on the other side of the world about this new muscle that we found, and you can describe exactly where it is, because we all start from here. Everybody okay? Now I want you to take a look at page 13 and look at those fancy names. Those are called regional terms or anatomical terms. I usually use anatomical terms. There's names there for stuff you didn't know there are names for. For my ANP1 Monday class, what's this region called? Mental. This is your mental region. How many guys knew that this was your mental region before you came to class? Nice. Yeah, we'll dredge it all back up. This is your mental region. Like, what the heck? What's this? That's not your elbow. You're close. This is antecubital here. This is, well, the cranial. Going like, what the heck is with all all these names. There's a lot of them on page 13. When you go through lab, you're going to get like 40 of those terms. My Wednesday lab people, we're doing this today. Monday lab people, you're already starting to learn it, right? Monday lab people, right? You already started this. You're not going to wait till the last day before class. This is valuable to learn because stuff is named after it. This is your brachial region, right? Well, the muscles here are your biceps brachii, your brachialis, and your triceps brachii. There's a brachial nerve that runs through there. Brachial artery runs through there. So once you learn these names, a whole bunch of other stuff is connected to it. This is your acromion region. There's also a bone feature there on your scapula that's called the acromion or acromion process. You need these words. You need to learn these words. That being said, I'm not going to directly quiz you on those words in this class. You're totally going to get quizzed in lab. I expect you to know them here. All right, fair enough? Okay. Directional terms. Again, Monday lab people, you should know all this. Superior and inferior. Does superior mean better?
No.
No. Superior means above, and inferior means below. Take a look at page 14. There's a nice chart. And be careful because superior and inferior are usually used on the head and trunk. Superior and inferior are usually used on the head and the trunk. My nose is superior to my mouth. My mental region is inferior to my mouth. I would not say my antebrachial region is inferior to my brachial region. Don't do that. We're going to use proximal and distal for arms and legs. Trunk and head, superior and inferior. Everybody comfortable? Anterior and posterior. See in parentheses, ventral and dorsal. You should be fluent in both of those sets of terms. You should be able to understand anterior is ventral and posterior is dorsal. Because you'll see it used different ways, different places. Like one sentence will be dorsal, the other sentence will be posterior. You need to switch back and forth between them. You need to know both. Anterior is towards the front of your body, posterior is towards the rear. Anterior towards the front, posterior towards the rear. Monday lab people, how do you remember that?
The dorsal fin?
Yeah, dorsal is in the back. If you were a dolphin, where would your dorsal fin be? Everybody make a dorsal fin. Go ahead, make it. Everybody make dolphin noises. Dorsal or posterior is towards the back. Ventral or anterior is towards the front. How many guys have tropical fish or aquarium? You know, in the picture, somebody got that little line of poop coming out. That's the vent. That's why this is the ventral side, because if we were fish, the poop would be coming out of here, out of the vent. That's where ventral comes from. Ventral and dorsal are really more biology terms than human anatomy terms, but they get used a lot. So we gotta know both. Everybody okay? Medial, lateral, and intermediate. First of all, don't worry about intermediate. Intermediate, like, is kind of in between. Lateral means further away from your midline. Medial means closer to your midline. Lateral is further away from your midline. Medial is closer to your midline. You can practice that. Go home, and get your little brother or little sister, get a Sharpie, and draw a line right down the middle, and you can practice medial and lateral. Make sure you use a Sharpie and not something that erases. Mom will get mad at you. Proximal and distal. The side proximal right is closer to my body then, in parentheses. Doesn't have to make sense, just do it. The side proximal right is closer to my body than. And the side distal, right, is further away from my body than. It's further away from my body than. That's what those words mean. Now you're talking about arms and legs here, not head and trunk. Doesn't make sense. This isn't proximal, this isn't distal to anything. Arms and legs. My antecubital region is distal to my brachial region. My antecubital region is further away from my body than my brachial region. My carpal region is proximal to my digits. My carpal region is proximal to my digits. My carpal region is closer to my body than my digits, my digital region. Does that make sense? Proximal and distal. All right, minded people, let's see how far along you are. My sural region is blank, my popliteal region. My sural region is blank, my popliteal.
Lateral?
It's gotta be
Oh,
proximal
wait,
distance,
no.
it's on my leg. Sural region is blank to popliteal.
Distal?
Distal, yes. My sural is my calf, my popliteal is the back of my knee. By the way, there's a popliteal artery, so if you know that's your popliteal region, then be able to name popliteal arteries. That's why these words are valuable. How many of you guys are starting to figure out, whoa, this is like a different language? Have you guys noticed that? Yeah, it's called Latin. You're learning Latin. By the way, to help you learn Latin, in the back of your book, last 5 pages, word roots, prefix, suffixes, and combining forms. If you start to approach this, you can see a word you've never seen before and look up the roots, prefixes, and suffixes and figure out what the word is. After A and P, partway through A and P1, you'll start to do this. By the end of A and P2, you can look at a word you've never seen and know what it means because you know the roots, the prefixes, and suffixes. If you approach this that way, it'll help you. If you know Spanish, it may help you too, because a lot of this stuff matches up. Superficial and deep. Superficial means closer to the surface. And deep means closer to the interior. It's not, he is so superficial, she is so deep, I just don't get it. That's not how it goes. Superficial is toward the outside. My skin is superficial to my muscles. My bones are deep to my muscles. Some of them. Does that make sense? All right. There's our anatomical regions. We talked about those. Body, planes, and sections. Take a look at page 15. A body plane or section is how you slice something up to look at. That's how you slice something up to look at it. And there's nice pictures there on page 15. Transverse is horizontal or cross-sectional. When you make a transverse section, you end up with a top and a bottom. You do a transverse or horizontal section. You got a top and you got a bottom. When you do a frontal or coronal section like this, slice like this, you end up with an anterior and a posterior piece. You end up with an anterior and a posterior section. And then if you do a sagittal plane, sagittal is like this, you end up with a right side and a left side. Now mid-sagittal is right down the middle, boom, right down your midline is mid-sagittal. Anything else is parasagittal, or you can just call it sagittal. All right? Everybody okay? Body cavities. We have spaces inside of it. Deep organs. You can even see some of those on 15, especially on the frontal and the transverse plane. By the way, when you have time, you should make time, take a look at page 16 and 17. We have some really cool imaging tools that we use now. There's amazing stuff. We can see inside the body without having to do exploratory surgery. We can see all kinds of stuff happening with all those imaging tools, and they're pretty neat. Way back in the dark ages, like in the 90s, they put something online. I don't even know if it's still available. I haven't looked at this in years. It's just popped on my brain. Let me see. Visible Human Project. Sometime if you want to search for Visible Human Project, the very first anatomy imaging tool, one of the kind of interesting and sort of weird anatomy visualization tools they did was back in the 90s. They took a guy who had been convicted of murder. He donated his body to science. If I remember correctly, they executed him, or else he just died of natural causes in jail. They put him in a block of gelatin and they chipped him, a slice at a time, and took pictures. So you could click, this is before, I think it's before YouTube. You can click and watch this movie and slice. You can see the insides of somebody for the very first time presented that way. So check it out, it's kind of interesting. It's a little interesting piece of internet trivia with Visible Human Project. They got a female too. I don't think the female was a convict. Let's see. Yeah, the male cadaver is Joseph Paul Jernigan, a 38-year-old Texas murderer who was executed by lethal injection. And he agreed to donate his body to science. So yeah, nobody used it anymore because there's much better stuff. All right, body cavities. Take a look at page 18. Body cavities are spaces where we keep organs. And of course, they're divided up. The dorsal body cavity is towards the back. Most of it is towards the back. The dorsal body cavity on that picture on 18 is the one in yellow. The dorsal body cavity consists of two smaller cavities, cranial cavity and spinal or vertebral cavity. Cranial cavity and spinal or vertebral cavity. Cranial cavity is where your brain is. And the spinal cavity is where your spinal cord is. In both lecture and lab, you must give me the most specific cavity name if I ask you to name a cavity. If I say what cavity is the brain in, you need to say cranial and not dorsal. Does that make sense to everybody? You gotta use the most specific cavity name. Ventral body cavity, that's the big one. That's the kind of reddish orangish one that's in there. That has a lot of subdivisions. We can divide ventral body cavity into thoracic and abdominal pelvic to start with. Thoracic cavity is above the diaphragm. Abdominal pelvic cavity is below the diaphragm. I don't normally use this thing, but it's here. This is the diaphragm. Diaphragm is a thin sheet of muscle connective tissue. What does it do in your body? Yeah, it helps you breathe. When you breathe, this actually drops down. Muscle contracts and it goes like this. But this divides thoracic from abdominal pelvic. Abdominal pelvic cavity consists of the abdominal and the pelvic cavity. There's not really any kind of membrane that separates them. They're just different places. Abdominal cavity is the big one, like right here. We all know where our abdominal region is. Pelvic cavity is down in between our coxal bones. You guys know you have coxal bones? What's another word for them? Hip bones, yeah. Or hip bone, fancy word for hip bones. No coxal. So that's the abdominal cavity and the pelvic cavity. I'm not going to ask you to differentiate between abdominal and pelvic. You can just call the whole thing abdominal pelvic, and I'm fine with that. The other one, though, there's some differences. In the thoracic cavity, if you look at page 18, there's a bunch of different cavities inside thoracic cavity. There are 2 pleural cavities. That's where your lungs go. Each lung goes in its own pleural cavity. There's a pericardial cavity in the middle. That's where your heart goes. Pericardial cavity is where you find the heart. And then, this is where I differ from some other instructors, the mediastinum. Mediastinum isn't really a true cavity. It doesn't have serous membrane. Mediastinum is more like an area. Like this area up here is the superior mediastinum. This area down here is the inferior mediastinum. It's an area like this. If you took a big coffee can and drove it into your chest, that would be the mediastinum, the area. But there's no membranes, there's no serous membranes to really make them cavities. So I consider mediastinum more an area than an actual cavity. If your lab teacher thinks it's a cavity, cool, go with it. You can argue either side. That's between you and your lab teacher. If you're in my lab, it's not a cavity. What else we got? Now, look at all those big fancy words there. Visceral and parietal this, visceral and parietal that. Holy crap, there's a lot of them, isn't there? Looks kind of confusing, doesn't it? There's an easy way to decode that. I'm going to skip around in the notes a little bit. We're going to talk about this because we're here. Skip it in the notes. It says serous membranes in the ventral body cavity in your notes. Everybody see that? Let's talk about a generic serous membrane. Serous membranes have 2 parts. Serous membranes have 2 parts. There's a visceral serosa and a parietal serosa. The visceral serosa is a membrane that is stuck to the organ. The visceral serosa is a membrane that's stuck to the organ. Viscera, anybody know what eviscerate means? If you eviscerate somebody, what do you do to them? You gut them, yeah. Anybody hunt? You eviscerate it, you pull the guts out. You have to field strip them first, because it gets pretty ugly. If you leave the guts in for a day or two, it's gross, it's really good. Visceral, actually on the organ. The visceral serosa, visceral membrane is actually on the organ. The parietal serosa, we left our notebook here and I'm going to steal these. All notes? Oh, here we go. The parietal membrane or parietal serosa lines the cavity where the organ sits. The parietal serosa lines the cavity where the organ sits. What organ is this? The heart. Give me a function for the heart. Pumps blood, beautiful. Alright? So this would be the visceral membrane around the heart. And this would be the parietal membrane around the heart. Does that make sense to everybody? Both of these membranes make fluid called serous fluid. Both of these membranes make fluid called serous fluid. Serous fluid is really important. Why? You're on the right track. You're correct, but I want more. Yeah, good. Prevents friction. It prevents friction and lubricates whatever it's around. How many of you guys seen like a Discovery health channel where they crack open a chest and you see a heart in there beating? It's working pretty good. If you run out of serous fluid, that hurts. Pericardial friction rub. It's very painful. It can cause damage. How many of you guys watched The Walking Dead for like the first 3 or 4 seasons before it got repetitive until the boring? It's okay if you watch it now, whatever. Do you remember when they were in prison and people were coughing up blood? They had pleurisy, which means they had an infection of their parietal pleura, the membrane around the lungs. They ran out of serous fluid around the lungs, and their lungs literally shredded by rubbing against the cavities. Serous fluid is important. Serous membrane system makes serous fluid. Visceral around the organ, parietal around the cavity. Now we gotta name them. This is a visceral pericardium because it's on the heart. This is a parietal pericardium because it's in the pericardial cavity. Does that make sense to you guys? Everybody's all right? Take a wild guess. And tell me what this organ is. Good. What's that serous membrane? Visceral pleural. Because it's on the lung. And the lungs are in the pleural cavity. So the membrane around the cavity where this goes would be the parietal pleura. And down here, visceral and parietal peritoneum, that's on all of them. Most of the organs down in here have a visceral and a parietal peritoneum. Does that make sense to everybody? Does that make more sense now? These organs are named for where they are. I'm sorry. These serous membranes are named for where they are. Visceral is named because it's stuck to the organ. Parietal is named because it's lining the cavity. Just where is it? Which one is it? You got all the names. Everybody okay? Questions? Good? Somebody has a question. No, you're not standing here shy. Pardon? Peritoneum. Good question. Peritoneum is the name of the membrane that covers your stomach, your small intestines, your large intestines, your liver, all of the stuff that's floating around in there. Question?
What's the difference between like the 3 fluids? So like
Pretty much all the same stuff. The only difference is where it's at.
area.
It's a watery fluid that's lubricant. It has hyaluronic acid and other stuff in it, which makes it nice and slippery. But the only difference is where it's at. So are we good with all the cavities and all the membranes and everybody's happy? Let's knock off the 9 abdominal pelvic regions. Take a look at page 20. You don't have to memorize those. The only reason I still talk of, they don't really use them anymore. The only reason I still talk about it is because it helps illustrate the idea that words mean things. This right here is your epigastric region. Epi means kind of above your gastric region, your stomach. So this is epigastric. These guys are hypochondriac regions. What's a hypochondriac? Somebody thinks they're sick all the time, they're on WebMD all the time. Oh my God, I got this disease all the time. No. Yes, but not here. Hypo means underneath. Chond, the C-H-O-N-D is our word for cartilage. We have cartilage connecting our ribs to our sternum. Hypochondriac is under the cartilage. Hypochondriac is under the cartilage. This is your umbilical region. You guys know what an umbilical cord is, right? You know the fancy name for belly button is umbilicus, right? So it's the region right here. These guys are lumbar regions, right and left. This back here is your lumbar region. These are iliac regions because iliac crests are here. That's a feature of the hip bone, the iliac bone. So this is the iliac regions, and this is hypogastric because it's below the gastric. Words mean things. The sooner you figure that out and start approaching these terms this way, the better off you're going to be. Now, back to what you really need to know. Page 19 shows you the quadrants, or quadrants. Left upper, left lower, right lower. Makes sense, right? In lab, you need to know which organs are in which quadrants. Not here. I expect you to know it here, and you need to know it for lab. Everybody good? All right, that brings us to other body cavities. Everybody comfortable with serous membranes, interventral body cavity, visceral parietal, serous fluid, pericardium, fluoroid, peritoneum? Everybody okay with those terms? You know where everything is? Now's a good time for questions, because there's probably 6 or 7 people who are going like, crap, I don't know. I hope somebody asks a question. Everybody's good? You see companies desperately try not to look at me, it's okay. All right, other body cavities. There are other cavities in our body. They're not big ones, but there are other body cavities. The oral cavity. You guys know what that is, right? It's your mouth. There is space in here. That's your oral cavity. The digestive cavity is kind of the rest of the tube. After your mouth, you have your esophagus, you have your stomach, you have your small intestine, you have your large intestine, you have your rectum, and you have your anus. One big, long, giant tube. You guys know your mouth is connected to your anus, right? Mm-hmm. Total connection. Technically considered to be outside the body. It's not sterile. There's lots of critters that live in there. Theoretically, you could swallow one end of a piece of string and hang on the other one, and eventually do that. When you pull the string out, don't pull it this way. Don't do that. It's all a big giant tube. That's your digestive cavity. Your nasal cavity, behind your nose. How many of you guys have all seen a skull, right? Is there a beak here like a nose? No, there's space. If you remove this, there's a hole there. Actually, 2 holes, nostrils. There's a there's a bony plate in between them. It's called your septum. It's also the perpendicular plate of the ethmoid bone and the vomer. And if you want to go from 2 nostrils to 1 nostril, big nostril, just do a lot of coke. Don't burn it all out. Don't do coke. Nobody does it anymore. Everybody's doing oxys and stuff like that.
I don't think I come back.
All right, I'm glad you know that. That's totally teaching.
Yeah, younger coke.
All right. And we do live in Florida. So, nasal cavity, orbital cavities. You got 2 of them. What goes in your orbital cavities? Eyes. middle ear on the other side of your eardrum, fancy word tympanic membrane. There's a cavity in there. And you got the three smallest bones in your body, your auditory ossicles. You actually have bones that help you hear. And then your synovial cavities. Synovial cavity is also called a joint cavity. Everywhere you have freely movable joints, there's a synovial joint. And there's a tiny little space there, filled with fluid. I normally talk about this when you do joints, and I'll forget I told you now and tell you again, but how many guys crack your joints? How many guys were told, don't do that, you'll get arthritis? That's not true. They've done studies, people who crack their joints regularly do not have a higher incidence of arthritis. They may even have a slightly lower incidence, but it's not statistically significant. So if you want to crack them, crack them. If you don't, don't. No big deal. All right?
What was in between orbital and
Your middle ear. Middle ear. All right, that is chapter 1. Normally I would steal 45 seconds from you, but questions, comments, concerns? Yeah. Here's my philosophy on exams. I don't know. But